Okay, so I already wrote a couple of things here, but today we're going to go over the non-homogeneous linear system. So how we solve the non-homogeneous linear system with the method of undetermined coefficients. So let me walk you through what I just wrote here, and then I want to point out that this lesson, to an extent, should be very familiar to you, because the method we are going to employ in order to solve the non-homogeneous system is it's the same method actually for single ODEs. You really have the same type of work basically as in the single ODE, but lucky you're going to do twice the amount of work, because since you solve systems, you're going to have two components to match. Now, be mindful of this. The examples that I pick in the homework, the problems, are purposely chosen so that you don't have too many coefficients to do by hand. So it will be, in the exam, it will be up to 4 coefficients to find, and even in that case, the system that comes up for finding these coefficients should not be too hard. So I'm not going to put, for example, problems that will require row reduction, because these problems tend to be too long when you solve these systems, and I don't want to deviate too much from the main idea on the differential equation side. Now, of course, if in life you have to do more complicated systems by hand, all you got to do is to just have more patience, but the method is really the same. So remember, the main theorem in the class still holds for a system, right? So if you have a system in the standard form, non-homogeneous this time, with f bar of t being the non-homogeneous function, the first part you're going to do the homogeneous part of the solution with everything you learned so far, with eigenvalues and vectors and all that good stuff, except that what you find in the first step, you're going to call that xh, because that's just the homogeneous part of the solution. Then the topic of today's class is how to find a particular solution for the entire system, and then of course at the end you're going to add the two, and that's the general solution of the system. So I'm going to start with an example here, and the method of undetermined coefficients, remember, works only if the f bar of t is made of those functions listed in the formula sheet in that table: exponentials, polynomials, sine and cosine combinations, constants, and so on. So those tip functions that are kind of similar if you differentiate or integrate them. Incidentally, there are other methods, by the way. There's a method of variation of parameters, which is not part of this class, but I may actually add it later after the class ends, just as a completion of this theory, essentially. Now, of course, there are many other methods which are not part of the class that I may add later, but for this class right now, we're going to focus just on the method of undetermined coefficients. So there is, though, one big difference from systems to single ODEs. And to understand how that works, I wrote this example here by components. You don't have to do that, by the way, when you solve it, but to make my point right now, I wrote this system by components. So if x bar is made of x of t, y of t, this will be the first equation, right? So 1 times x plus 1 times y plus 3 to the t minus 2. And the second equation, 4x plus y minus 5. Because the more important remark, that make sure you write it down after I mention what it is all about, is that when you choose xp, you have to be careful to match both entries of xp to match both entries of f bar of t. So rather, each entry of xp should take into account, or should match, both entries of x or f of t. So for example, a mistake here is to assume that the particular solution xp would be in the form of combination exponential plus constant on the top and constant on the bottom. So that is not general enough. You cannot assume that y does not need an exponential simply because f bar of t has a constant only. And the reason is, think about that this is a system. X and y play a role in both equations. Again, we cannot assume that y doesn't need, in this combination, both exponentials and a constant. So you have to treat this as a system, basically, right? So to make sure you're general enough when you pick xp, you got to make sure that each component of xp will match both components of f bar of t. So that is the main remark that you have to keep in mind before you move on. It's not difficult at all, but be aware of it, because if you forget it, it's very easy to make this lack of a generalization mistake, so to speak, by picking choices independently for both of those entries. So to proceed with this example, the correct choice then for xp would be first component matches both components of f bar of t, so a to the t plus b, right? A combination of an exponential plus a constant. And similarly, the second component again will match both entries of f bar of t with different coefficients. We cannot assume they're the same, but in the same manner, right? Exponential plus a constant. So when you choose xp correctly, these entries should basically be the same, but with different coefficients. So same format for both entries with different coefficients, but the same format matching both entries of f bar of t, of the non-homogeneous term. So once you make the choice correctly, now you basically proceed with finding the coefficients by extracting the matching equation. So you're going to plug in xp, this format, into the system, do some algebra, and then extract the matching equations. So on the left side, we're going to plug in a to the t plus b, c to the t plus d prime. And on the right hand side, of course, the matrix of the system 1, 1, 4, 1. And x bar, which is a to the t plus b, c to the t plus d. I didn't actually provide the homogeneous part of the solution yet. I'll do that later. Let's just focus on finding the particular solution, because normally, remember, that's your starting point, right? The homogeneous part. Okay, so plus the non-homogeneous term, which is 2e to the t minus 2 minus 5. So be patient in the beginning with your algebra. Don't forget to take the derivative on the left. So on the left, you're going to end up with a to the t, c to the t, right, after you take the derivative. And on the right, perform carefully the matrix operations. Matrix multiplication first, and then addition with the non-homogeneous term. So 1, remember, this is still a column. Doesn't matter how large it becomes because of this format. You still have 2 by 2 times 2 by 1 matrix. So row 1, column 1, right? So 1 is multiplied by the entire entry, a to the t plus b, plus 1 times c to the t plus d. And then you continue, if you want, at the same step with the matrix addition, plus 2e to the t minus 2. Second row, second component, right? So 4 times a to the t plus b, plus 1 times c to the t plus d, and then minus 5. So basically you have to write carefully, one column on the left, one column on the right, because then you can match entry 1, entry 2. So how do you extract the matching equations? Well, each entry will provide you 2 equations, because on each entry, when you match them, you're going to then further match the coefficients of the functions that appear in each entry. So for example, when we match entry 1, well, we have to match the coefficient of e to the t. It's a on the left, and on the right, don't forget any piece here. The coefficient of e to the t, if you pull out e to the t, becomes a plus c plus 2. Then the second piece to match is the constant term. There's no constant on the left, which means it's 0. And the constant on the right side comes from b, d, and minus 2. Moving on, we match now the entry 2. Again, e to the t, the coefficient of e to the t on the left is c, and on the right is 4a plus c, right? So the coefficient of e to the t comes from these two terms. And then finally the constant, 0 on the left, and the constant on the right is 4b plus d minus 5. So if you do everything correctly, you should have, again, as many matching equations as the number of coefficients to determine. And as I mentioned before you run with a big tool like a Gauss-Jordan elimination for systems, larger systems, pay attention, because just by grouping some equations, you can solve it quickly. So if you look carefully at the first equation, you realize that I can quickly find C. So I will obviously start with that one. So from the first equation, I get C equals minus 2. Look carefully at the third equation. You can cancel C, which means obviously A should be 0. So you already found two constants, two coefficients. And now you can form a 2 by 2 system within B and D. And you can solve that by elimination. So B plus D is 2. 4B plus D is 5. I can subtract the 2. 4b minus b is 3b, 5 minus 2 is 3, and that gives me b equals 1. And if b equals 1, from the first equation, let's write it here, 1 plus d equals 2, I get d equals 1. Okay, so when everything is said and done, your particular solution that you just found that matches the whole thing is what? A e to the t plus b. A is 0, b is 1, c was what? Minus 2 e to the t, and then plus d, which is 1. Okay, so it's worth pondering a little bit here to reinforce what I just told you before, that you can't assume beforehand that your particular solution does not need an exponential on the second component. See, in retrospect, once we took this in this most general form, not only it turns out that you actually needed e to the t on the second component, so you needed to have this assumption, but it so happens that the first component actually is a constant. So you didn't need e to the t on the first component. So you have to treat this as a system, and it's not like once you solve for A, B, C, D, they will all be non-zero. Some of them can be 0, like in this case. Some of them may not be 0. Who knows? You cannot assume a priori. The problem is you have to assume the most general format before you proceed with the method of undetermined coefficients. And the most general format suitable is the one that matches both entries of f bar for each entry of xp bar. And then, of course, we'll see after we find the coefficients whether some of those will be 0 or not. And that completely depends on what you have here and the relationship between other coefficients in the system. So, just to save some time here, I'm going to actually provide the homogeneous part of the solution here. Take some time if you want and solve the homogeneous part just as an exercise. So you can pause the video and just solve x prime equals 1, 1, 4, 1 x bar, although I think it's done in some earlier examples, but you could solve it to confirm. The homogeneous part of the system in this case is going to be C1 1, 2 e to the 3t. So this will be eigenvalue 3, eigenvector 1, 2, and C2 1 minus 2 e to the minus t. Okay, so that will be basically your first step if you were to do the problem from scratch, which means the full general solution of your system will be obviously the homogeneous part in terms of these arbitrary constants C1 and C2 plus the particular solution that you just found. Okay, so finally this is the general solution of your system. Now, of course, in the name of being a little bit more efficient, in the exam sometimes I may say, okay, here's the homogeneous one, find a particular solution, or just take a format of the particular solution but don't solve for it. So you gotta have to pay attention to see if I only ask a specific portion of the problem and not the whole problem from top to finish, which could be rather long, as you'll see in the next part, because just for the record, I'd like to do one problem from top to finish. One thing I want to mention here and add to this, remember, we always can have initial value problems. Always deal with that at the end. Okay, so the initial value problem, if it's given, refers to the full solution, not just the homogeneous part. So let's say you have an initial value problem with x of 0 equals, let's see, have the example here with nice numbers. So let's say x of 0 equals 1, 3. Okay, so you deal with that at the end to find C1 and C2, and then don't forget to also take into account this part of the solution when you set up t equals 0. So you have to be careful with that, right? So let's do this little system here. X of 0 equals 1, 3 means the following. X of 0 is C1, 1, 3. E to the 0 is 1. Plus C2, 1 minus 2. E to the 0, which is again 1. Then plug in 0 here on the non-homogeneous part, so that becomes 1 minus 1, because it's minus 2 times 1 plus 1. So that's 1 minus 1, because it's minus 2 e to 0 plus 1. Just want to make sure you see where it comes from, and that's equal to 1, 3. So this is where you form the system in C1 and C2. So what is the system in C1 and C2? Well, it's going to be C1 plus C2 plus 1 equals 1. 3C1 minus 2C2. This is again minus 1, minus 2 plus 1 equals 3. So move these constants to the right. So the system now is going to be C1 plus C2 equals 0. 3C1 minus 2C2 equals 3 plus 1, which is 4. So how do I do this quickly? Let's see, we can so 3C1. Why did I put 3? I'm sorry, it's another typo here. Yeah, sorry about that. Let me fix that quickly. I put a 3 instead of a 2 for some reason. So this is C1, 1, 2. C2, 1 minus 2. 1 minus, okay, 1, 3, that's all good. So this should be 2. And this should be 2. 2C1 minus 2C2 equals 0. So let's actually cancel by 2 the second equation. So C1 plus C2 equals 0. C1 minus C2 equals 2 if I divide by 2. So if we can eliminate quickly C2 by adding the 2. 2C1 equals 2, and that gives me C1 equals 1. So that's the first constant. And from the first equation, obviously C2 equals minus 1. Okay, so your solution to the initial value problem in this case will be this stuff, but with C1 equals 1 and C2 equals minus 1. So in the next part, we're going to go over one example from top to finish. One thing I want to mention before we move on, in this case with the systems, we're not going to deal with the duplication. So duplication with the homogeneous part can still happen. So duplication with YH, with XH, with the homogeneous part, can still happen and is handled in a similar way. As in the single ODE without extra t. I do not want to make it a requirement, so I'm not going to go over in the case of systems. So I'm not going to go over the duplication case for systems, and you won't have that type of problem in the test. But just as I mentioned that it can happen when the non-homogeneous term is duplicating the homogeneous one, and it's usually handled in the same manner, but obviously the whole computation is more tedious when that happens. So stay tuned for the next part. We're gonna go over one extra example, and this time again for completion we're gonna start by solving the homogeneous part and then finishing up with the particular solution. So stay tuned.